Welcome to The Explainer, where we break down the big ideas. Today, we're going to pull back the curtain and look at the hidden formula that lets an AI learn, plan, and, well, pretty much master any challenge you throw at it.
So how does an AI do that? How does it look at a million possibilities and just pick the right one? Well, in this explainer, we're going to dive into the core logic that lets a machine find that one perfect path, whether it's winning a game or, driving a car.
And trust me, this is not science fiction. This very same logic is the engine running some of the most advanced AI we have today. We're talking autonomous helicopters, robots that can walk, even the systems that route all of our internet traffic. So, how does it all work? Let's get into it.
To really get this, we're not going to start with a bunch of complicated code or anything like that. Nope. We're going to start with the really simple quest.
So, meet our little agent. Its mission, should it choose to accept it, is to get to that green square. If it makes it, it gets a +1 reward. But it has to avoid the red fire pit, because that's a -1 penalty. Oh, and the gray squares? Those are walls. Can't go through them.
Okay, so before our agent can do anything smart, it needs a map of its world, right? You wouldn't explore a new city without one. In AI, this map has a kind of fancy name, a Markov decision process, or just MDP for short. It's basically the language the AI uses to see the world.
Now, what's so powerful about this framework is that you can use it to break down almost any problem into these 5 key parts. It gives the AI a structured way to look at things. For our little maze, we're just going to focus on the first 3 big ones: states, actions, and rewards.
All right, first up, states. We use a big S. And all this means is asking the question, where can I be right now? For our agent, every single one of these squares on the grid is its own unique state. That's it. Simple.
Makes sense, right? Now, in each of those states, our agent has a set of possible actions it can take. We'll call that A. In this case, it's just a simple list of 4 moves it can try.
And this might be the most important piece of the puzzle: rewards, or R. Think of these as feedback from the world. It's basically the environment saying "good job" when it finds something good, or "uh-oh, don't do that again" when it hits a fire pit. It's how it learns what to aim for.
Okay, so our agent has its map, its MDP. It knows the states, it knows its actions, and it knows the rewards. But so what? How does it actually use that map to find the best path? Well, the secret is this really powerful idea from a mathematician named Richard Bellman, way back in the 1950s.
It reminds me of this quote from the philosopher Søren Kierkegaard. It's this wild idea that to figure out the best way forward, you have to start by thinking about the end.
So instead of just letting our agent wander around and hope for the best, the Bellman equation gives it a kind of superpower. It allows it to calculate the true value of being in any spot on the map. And the trick, the real genius of it, is that it works backwards from the goal. Let's actually see this in action. We're going to start at the finish line, the green square. What's the value of being there? Well, it's easy, right? It's the +1 reward you get for landing on it. So its value is just 1.
Now, here is where the magic happens. That white square, the one right before the goal, all of a sudden it becomes valuable. And why? Not because of anything in that square itself, but because of where it leads. It's one step away from that guaranteed +1 reward. Its value comes from the future it promises. But hold on a second. You might be thinking, if we just keep copying that value of 1 all the way back, every square on the path will seem equally good. And you're right, our agent would still be totally confused. We need a way to make rewards that are closer seem better than rewards that are far away.
And that is where our last piece of the puzzle comes in, the discount factor. We call it gamma. It's a really clever little trick. It's just a number that's a little less than 1, say 0.9. And what it does is it tells the AI, hey, a reward you can get right now is better than that same reward way off in the future.
So check out what happens now. As we work our way backward from the goal, the value gets chipped away just a little bit at each step. The square right next to the goal is worth 0.9. The one before that is 0.81. You see what's happening? We're creating this beautiful slope of value, a gradient that our agent can just climb uphill to get to the goal.
Now, this whole process of calculating values isn't just random. It's all done by specific algorithms. You have one called value iteration, which basically figures out the value of every single square on the map first. Then there's another called policy iteration, which is more like, let's start with a rough guess for a path, and then just keep making it better and better.
But the key is, they both use that same time-traveling, discounting logic to solve the map.
So, after all that math, all of that working backwards across the entire grid, what do we actually have? What does our little agent end up with?
It gets this, an optimal policy. And honestly, the best way to think about it is like the ultimate cheat sheet, a finished treasure map. No matter where our agent is on the board, there's now a single clear arrow pointing and saying, go this way. The agent doesn't have to think or guess anymore, it just has to follow the arrows.
And that's it. That's the big reveal. This simple, elegant map of arrows, that is the brain that's powering all that incredible stuff we saw at the start. It's how a robot learns to walk. It's how your phone company routes your calls. It's all just following the arrows.
So the next time you see an AI do something truly incredible, you'll know the secret. You'll know it's not some unknowable magic. It's just following a map that it built by looking into the future and working its way back. Which kind of makes you wonder, doesn't it? If any decision can be mapped this way, what's the next complex human skill AI is going to master?